Okay, now we get to go back to our definitions here. We've kind of seen this term before. So an nth order linear differential equation of the following form is considered to be homogeneous. Of note, it's the derivative piece starts with the nth degree and then n minus 1, then n minus 2, and then all the way down to n, and then just the function itself. If we don't have that order, we consider that to be non-homogeneous. So what we're referring to here, so here I've got the double prime, the prime, and the y. That makes it homogeneous, but here I've got triple, double. I skipped the prime, so I'm missing a piece that would make this homogeneous. So hopefully that makes sense. And then another definition, differential operator. In calculus, differentiation is often denoted by the capital letter D, that is dy over dx equals dy. The symbol D is called the differential operator. Because it transforms a differentiable function into another function. Okay, so this is kind of like a shorthand notation. So let's take something like the differential for cosine 4x. Essentially take the derivative. I end up with a new function of negative 4 sine of 4x. Let's say I have 5x cubed minus 6x squared. And the differential operator would just give me 15x squared minus 12x. Higher order derivatives can be expressed when this denotation. So what we're used to, maybe something like this, where it's d dx of dy dx, would give us d squared y over dx squared. Right, so in this new notation, that would be d times dy would be d squared y. So in general, what we refer to as the nth derivative, we can rewrite simply in this notation here. Okay, so the intention here is just to introduce some new notation that will make our lives a little bit easier when we're solving some of these higher order differential equations. So let's just take an effort at defining what the notation is supposed to represent. So in general, we would define the nth order differential operator or polynomial operator to be in that pattern. So the D again refers to the differential equation element. As a consequence of two basic properties of differentiation, so the fact that I can take the derivative of a constant times a function allows me to factor out the constant. So, and the fact that if I have a linear combinations of two functions, that I can essentially take the derivative of each individual function. The differential operator L possesses a linearity property, meaning L is an operating on a linear combinations of two differentiable functions is the same as a linear combination of L operating on individual functions. In symbols, this means that think of it like distributive property. So I can distribute the derivative in certain situations, just like I can factor out certain constants. So anything that follows this nth order differential operator we refer to as a linear operator. Any linear differential can be expressed in this denotation. So say, for example, we take the differential equation of y double prime plus 5y prime plus 6y equals 5x minus 3, and I can rewrite this using that differential operator. So d squared y plus 5dy plus 6y equals 5x minus 3. And in that sense, I can factor out a y from all of my terms. So that would mean d squared plus 5d plus 6 times y equals 5x minus 3. Okay, so the superpositions principle states that if I have a set of individual solutions, then sets of linear combinations of those solutions will also be solutions to the original equation. So I guess that's a little too general. So let's say I've got a series of individual solutions to a differential equation. Then there should exist some constants of C1, C2, C3, blah, blah, blah. That would also make that true. Let me kind of come down here to the example. Hopefully this will make sense when I explore this with you. So I've got a differential and I've got two potential solutions. So the claim is that the general solution would be something with C1, C2 of those two initial solutions. So let's first verify that the two given solutions are actually solutions, and then we'll look at the individual, then we'll look at the general combination of the two. Okay, so let's start with y1. So y1 we said was x squared, so then the derivative of that would be 2x, and the second derivative would be 2, and the third derivative would be 0. So then let's substitute those expressions in and just verify that everything is on the up and up. So x cubed times 0 minus 2x times 2x plus 4 times x squared equals 0, and that looks pretty good. So that's going to give me 0 equals 0. Okay, so y1 definitely checks for that. Alright, so let's check the second one. So we want the first derivative, which is x squared times 1 over x plus ln of x times 2x. And I think that's worth taking a second to simplify. So that's x plus 2x ln of x. And then I want the second derivative, which is 1 plus 2x times 1 over x plus ln of x times 2. And let's pretty that up. Let's see, that is 1 plus 2 plus 2 ln of x. So that's just 3 plus 2 ln of x. And let's get the triple. So that's going to be 0 plus 2 times 1 over x. Okay, so let's evaluate that. So x cubed times 2 over x minus 2x, y prime was x plus 2x ln of x plus 4y. And y was x squared ln of x. Alright, so that is going to give me a 2x squared at the beginning, which is going to cancel out with that other 2x squared. Then we got 4x squared ln x plus 4x squared ln x. Okay, so far we look pretty good. Okay, so does it make sense then that the general C1, C2 linear combination of these would also satisfy that? And let's go find out. Alright, so I'm going to do a little bit of teacher magic and speed up the derivatives here so you don't have to watch the mundaneness of this. So 3, 2, 1. I feel like there should be fanfare. There it is. So you can kind of look over through the derivatives. Feel free to pause this if you want to convince yourself that those are the correct terms. Additionally, if we verify, evaluate it in the initial function, we do in fact get all the terms to cancel out. So I'll kind of scroll up and show that everything cancels out. So yay, it works.